Sorry, I was muted there. Welcome to class for Wednesday, May, whatever today is, May 6th? We'll go with May 6th. This is the second to last class, so we are right at the end. And so for today and Friday, we're going to do some review. And I think the best way to do review is I've just collected a whole bunch of problems. These are all problems that are test question rejects for one reason or another. Either they were too complicated or had something that might be confusing in them, or just I didn't like them for some reason. But these are basically questions that are leftovers from times when I've been writing exams. And we're just going to go through them. And, we'll work through them and ask questions and talk about concepts and hopefully review things for the end of the semester. So the goal today really is to try to at least start on reviewing the entire class for the whole semester, which, is just a small thing. Okay, reminders. So everything is due Friday. Everything is due Friday. I'm going to say that one more time. Everything is due Friday. I decided not to do video experiment number 9. You guys have enough going on in your lives. You don't need to do that. But it's a shame because it's, it's lovely. Grades. So as I've mentioned several times, this is all uncharted territory in terms of figuring out how to do your grades. And I've asked for your patience, and you guys have been extremely patient with grades, but they should start appearing on Blackboard. So you should check Blackboard regularly over the next week or so. If you find mistakes, and it is almost guaranteed that there will be mistakes, if you find something that doesn't look right or you just have a question about, please bring it up with me as soon as possible. If you send me an email, 3 weeks from now saying that your grade on homework 4 is weird, that's going to be really tough because we will have already submitted grades. But if you send me an email tomorrow saying my grade on homework 4 is weird, then we can, talk about it and figure it out. Post-test. There's a post-test. I forgot to send out the email. I'm going to do that while I'm talking here. There's a post-test. You should complete it because if you do complete it, you will get 5 beautiful extra credit points on homework, which is not a lot, but it's enough to, sort of hopefully make it worth your while. The post-test, again, is not, test is the wrong word. It's not testing you so much as it's testing me. It's my way of checking what topics I sucked at teaching this semester. And there will be probably many of them. But this is particularly useful for me because it is almost guaranteed that some pointy-haired administrator at some point in the future is going to look at this and say, oh, online is so much cheaper because we don't have to have buildings and we can put 20,000 people in a class, and why don't we just move everything online? And it's useful to have some hard data that says, no, that's a horrid idea. You should never do that. Because look at, I have data. I did a post-test, pre-test, post-test on these students. It did not go well, right? I have solid data that backs that up. Okay, so other things. The final. Sign up for the final. I've been getting a lot of emails from people asking what time they signed up for. I will post a schedule of everyone's final times on Blackboard, I don't know, in the next couple of days. So again, be checking Blackboard regularly. I'll have that up by class on Friday, and you guys can. can see when you signed up for. Hopefully you know when you signed up for. I already know there's one person who signed up twice. So there'll be a few hiccups and things we have to change, but for the most part, this has gone fairly smoothly. Okay, any questions about course administrative gobbledygook? Wonderful. Let's talk about physics. So the deal was that if you wanted to solve one of these things and then present your solution, then I'd give you extra credit. So if you've got a solution, I'm just going to start at the beginning here, and if somebody wants to jump in and present, say something. So first question, anybody want to do this one?
Is both beanbags end up with zero velocity, because if they both have the same mass, but they have completely different momentums, and if you use conservation of momentum and the collision is completely inelastic, then they're still going to have momentum because one of them is going twice as fast, and so it'll go in that direction. And if the collision is completely inelastic, they bounce off each other, and then they both have velocity. So.
Okay. Did everybody get that?
Yeah.
All right, let's do one thing here. So first of all, I just dropped the link to the slides into the chat. Hopefully you already have it because you have been studying diligently. But if you don't, it's in the chat. Let me do this. Okay, so Davey, you're up on this. Here's a whiteboard. I want you to draw what's happening here. Okay, it appears we have two beanbags. One has velocity v. That one has velocity minus 2v because it's going the other direction. Okay. They both have the same mass.
So if they both stick together after the collision, you just have one big beanbag that's going this direction with approximately negative v velocity. And then that has 2m because both of them, that's if it's completely inelastic because they stick together. And then with the momentum, they're going to shoot in the direction of the one that's going faster. And then if they're completely inelastic, then this beanbag will be moving basically either in this direction but slower than it was going, or in this direction, and then this other beanbag will be going in the opposite direction that it was starting.
Okay. So you're saying the first beanbag ends up moving backwards, right? That's happening in both of your cases that you've drawn here.
Yeah.
Right? Okay. The second beanbag ends up moving backwards. Well, that could happen here, right?
Yeah.
If they bounce off of each other.
Yeah, if they bounce off of each other, but that beanbag is still going in that direction because it started with minus 2 times the velocity.
Mm-hmm. So they could just trade momentum, right?
Yeah.
They could just trade velocity.
Yeah.
That would be a perfectly elastic collision, right?
Yeah.
If this guy was moving backwards at v, here, let me turn on a little spotlight thing. If this guy's moving backwards at v and this guy's moving backwards at 2v, All they've done is traded velocities, and because they have the same mass, that has the same momentum, same total momentum, same total kinetic energy. So there's our perfectly elastic collision. Okay. One of the beanbag ends up with 0 velocity. How could that happen?
I didn't really think it would, but it asked for the one that physically couldn't happen. But I mean, theoretically, one could end up with all the velocity.
So we have sort of two extremes here, right? We've got the two extremes. I'm going to erase your arrow there, right? So your two extremes are they stick together, right? And they're both moving this way, right? They're both moving to the left. Or they bounce off of each other, and this one's moving to the left, and this one's moving to the right. So we can imagine a case between those two, right? Where some of the energy gets lost, but not as much as could get lost, right? Where maybe one of the beanbags stops, but the other one keeps going.
Yeah, because you can make the conservation of energy, you can do that with one beanbag stopping and one going away with all of the energy.
Right, because initially, if we add up the momentum, right, we had mv minus 2mv. So our total momentum before the collision was just minus mv, right?
Yeah.
Well, so down here, we have to have that same amount of momentum. So actually, in order for this to be true, here I'm gonna, it wouldn't be negative v, it would be
negative
minus v over 2, right? Because we've got 2m, and it has to add up to mv. So there you go. Okay. And in our other extreme case, right, this guy just has negative 2v, and this guy just has v. Oh, wait, negative v. I've got the wrong. Oh, no.
He would have v.
Right. V. Yep. Okay, so somewhere in here, we could dream up a case where, let's say this guy was at rest, this beanbag on the right, and the beanbag on the left was moving with negative v, right? That's legal.
Yeah.
It conserves momentum. It doesn't conserve energy, but it doesn't have to always conserve energy. So so Davey is absolutely right. The one you can't do is that both beanbags end up with 0 velocity. Because if both beanbags have 0 velocity, then you have no momentum after the collision. And you can't get rid of momentum, right? Can't happen. Can't get rid of momentum. No matter what these beanbags do in their collision, no matter how elastic they are or how inelastic they are, we're going to have some momentum. And that momentum, you can't hide it. You can't, you can't make it go somewhere, right? Energy you can hide. Energy you can make go into heat or sound or light or, chemical potential energy or whatever. But momentum you can't. All right, good. Okay. Questions, comments, concerns? All right. Let's go to the next one. Oh, by the way, there's a limit of 1 per person on these things. So you can't just rack up like 1,800 extra credit points. Anybody want to do this one? Oh, I'm not sharing it. You can't see it. There we go. Anybody want to do this one? No takers? All right. Then let's work on it. So let's draw. So let's see here. They've got the free body diagram over here, right? And they gave you the hint, consider the torque about the mass M, right? So there's mass M. So it's telling you, make your center of rotation there. What kind of problem is this? I'm going to start playing Jeopardy music in the background.
It's a torque problem.
Yeah, it's a torque problem. Specifically, it's a equilibrium problem, right? Because we want this thing not
Yeah.
to move. So in order for it not to move, in order for static equilibrium to be true, we have to have two things, right? The sum of the forces has to equal 0, and the sum of the torques has to equal 0. And this thing's giving us a hint that we can make our lives a little easier if we think about the torque side of that problem. So if we want to do torques, we need a center of rotation. And because this is a static equilibrium problem, when nothing is rotating, it's not rotating about anywhere, right? Which is an obvious thing to say, but it makes our problems a lot easier or harder depending on if we use it properly. So it gives you the hint, consider the torque about the mass M. So we want to make our center of rotation right there, which means our radius vectors look like that. And it's a little overkill on the radius vector. Let's get rid of that. How do I change that? There we go. Okay, so there's a, well, no, I'm just erasing things. Okay, so here's our radius vector. That's a more reasonable radius vector. There's one radius vector. Let's do the other one in a different color. I'm feeling orange today. All right, there's one radius vector. Here's the other radius vector, right? So let's call this guy our L, and I can't make this, I can't make it a subscript, but imagine it's a subscript. And this one R, right? Okay, now what do we do? I need the sum of the torques to equal 0. So how do I get the torques from these? I have forces. I have the radius vectors. How do I get a torque?
I think Davey just said something. I don't know if you heard him.
Oh, I didn't. Sorry, what did he say? Davey, I'm not getting your audio for some reason. I'm not sure if it's me or you. He's putting it in the chat. All right, cross product, force and radius. Excellent. So, excuse me. Whew. So we need to take a cross product, right? Because that's how we get a torque. So we come over here to our radius vector for the left side force. We put our fingers in the direction of the radius vector and we make them curl in the direction of the force vector, which means that the torque is pointed pointed into the screen, right? So that means that our torque over here, the radius vector wants to make, the torque wants to go this way. It's a really great arrow. But it wants to make the board rotate clockwise. Okay, how about over here? Well, same game. Put our fingers in the direction of the radius vector, curl it towards the force vector, and our thumb points in the direction of the torque. So the torque is out of the screen, which means it wants to rotate
Counterclockwise.
that way. Yep, counterclockwise. All right, so if we write out the math on this, right, I want them both to equal 0 when I add them up, because that's static equilibrium. So I have my two torques. I have the torque from the left-hand side, which is, which way do you want to call negative?
From going left.
So clockwise?
No, I mean like counterclockwise.
Counterclockwise. Okay, so clockwise is positive, which means the torque from that force on the left is positive. And because the force vector and the radius vector are perpendicular, we can do the really easy version of the cross product. We don't have to get into angles or components or, determinants of matrices. We can just say it's the radius of the left-hand side times the force on the left-hand side. Okay? And now for the right-hand side, it's the same game, except for this one's negative. And so we've got the radius on the right times the force on the right. Okay, now it wants the ratio of the forces. So we can get that if we move the second term over to the other side, which will give us that. And now all we have to do is divide both sides by RR and FL. And if we do that, we get FR divided by FL equals RL divided by RF. And because RL is 2/3 of times the length, and RF is 1/3 times the length, right? That's 2/3 divided by 1/3, which is just 2. So in this configuration, it puts twice as much force on the right-hand side as it does on the left-hand side. So the answer is D. All right, how are we feeling?
Can you explain the last step that you did, the 2/3 and 1/3?
Sure. So RL is 2/3 times the length, right? Let me clean this up a little bit because it got a little crazy here. Go away. I killed it all. That wasn't what I wanted to do. Can I undo it? Okay. I can't just get rid of the last line, but let me come down here and start over. And start from the second line, right?
Okay.
So, or the third line. I said FR divided by FL was equal to RL divided by RF, right? So that means that FR divided by FL is, well, RL is 2/3 times the length, right? So this is 2/3 times L divided by, and RF is 1/3 times the length. Wait, hold on. I got something confused here. This should be RR. I don't know what RF is. All right. And this is 1/3. Well, 1/3 times the length. Okay. The lengths cancel out, and I get 2/3 divided by 1/3. The 3's in the denominators of both the top and bottom cancel. And so I get 2 divided by 1. So this is just equal to 2. All right, how we feeling?
Better.
Good. All
I think
right.
I think it was like the coefficients that you changed them up that threw me off.
All right, I'm going to clear this thing off. And we'll go on to the next one. Oh, no. Oh, I have to go back to the mouse. That's how I do it. All right. Anybody want to take this one?
I'll do it. I'll do that one.
All right, all yours. Do you want the whiteboard?
Yeah, I think that'd be better.
All right. So let me read the question real quick, and then I'll switch it over to the whiteboard. Okay, so when a bullet strikes a bulletproof vest, it is designed to have a perfectly inelastic collision so that the bullet and the vest and the person wearing the vest get stuck together. Suppose a test dummy wearing a bulletproof vest has a mass of 70 kilograms and is stationary. During testing, the vest is shot with a bullet that has a mass of 12 grams and is moving at 440 meters per second. How fast would the dummy be moving immediately after getting shot? So I'll turn it over to the whiteboard here and walk us through it. Oh, I got to clear the whiteboard. There you go. All yours.
Great. So to start off, I did a before, I don't know, it's blue. I did a before picture and an after picture. So the before one looks like the bullet and then the dummy. And the bullet is traveling at velocity b. And the dummy is stationary, so it's not moving at all. Then you have after, where the bullet and the dummy are together and they are traveling at a velocity, I'll call it d. So velocity, velocity d. So then I looked back at some of the inelastic collisions that we did, and we were given a formula. So V2 is equal to M1 V1 over M1 plus M2. So I used that one, and I just plugged in the numbers. So V2 would be, in this case, VD. This is after their shot, is equal to the mass of the bullet, which is 12 grams, so 0.02012 kilograms, times the velocity of the bullet, which is 440 meters per second, divided by the masses added together, so 70.012. that comes out to be 0.08 meters per second. So that's what I got for the velocity of the dummy and the bullet afterwards.
Great questions. I have a question. How on earth do you write so well with your mouse?
I don't know, just practice.
I'm terrible at that. Okay, so where did this formula come from? I mean, the
Oh.
book, but where did the book get it?
It's, I'm not sure what, does it have to do with momentum?
Yes, it definitely has to do with momentum.
Yeah, so then it'd be the momentums has to be equal to each other from the beginning to the end. So if you just solve that for the final velocity, you get like this huge equation.
Yeah. So if we take the momentum beforehand, right? It's just the mass of the bullet times the velocity of the bullet. Here, let me type that out. So the momentum beforehand is just mass of the bullet, well, mass of the bullet times velocity of the bullet, right? And afterwards, it's just well, our masses are now combined, right? So it's the mass of the dummy plus the mass of the bullet. And our velocity is just the velocity of the dummy, right? So if we set these two equal to each other and solve for the velocity of the dummy, we get this lovely equation that you wrote, okay? So perfectly inelastic collisions where things stick together. Remember, any collision where things stick together is a perfectly inelastic collision. So a perfectly inelastic collision is one where we can just use conservation of momentum. We can just write the momentum before and the momentum after and solve for our final velocity, and we get how far it's going to go. Okay, so hopefully none of you have ever been shot while wearing a bulletproof vest, but I'm guessing everybody is aware that it really hurts, right? And this seems to say that all that's going to happen to you is you're going to get pushed backwards at 8 centimeters per second, which is not very fast at all. So what's missing in our physics here? Why on earth is it much worse than that to get shot even while wearing a bulletproof vest?
It's concentrated in a small area.
Yeah, the problem is that it doesn't actually collide with all of you, right? It collides with your chest or, a couple inch radius of your chest, right? And so that piece of your chest ends up moving backwards much faster, which is a problem because the rest of your chest isn't moving backwards that fast. And so you start ending up with problems, right? But that's more fun for later. For now, we'll just assume that. Part of the reason that a bulletproof vest works is that it spreads out the contacts, right? Instead of the bullet hitting, a teeny spot on your chest, the bullet hits a teeny spot on the bulletproof vest, and then the bulletproof vest hits a big spot on your chest. So, all right, good. Well done. All right, let's shut down our whiteboard here and go to the next problem. All right, next problem. Suppose you have a cargo rocket being launched that has a slow 10 radians per second spin. The moment of inertia of the rocket is initially 1,000 kilograms per meter squared. During launch, a bolt fails and some cargo comes loose, which causes the moment of inertia to increase to 15,000 kilogram, or I'm sorry, 1,500 kilograms per meter squared, or kilogram meter squared. Assuming no outside torques were applied to the rocket, how much work was done on the spacecraft? Anybody want to take this one? This is a good rotation problem. Okay, how many of you have seen The Martian or read the book?
Saw it.
This is what happened in the movie, right? Remember they're launching the food rocket to try to save the guy on Mars, right? And they, the launch is going well, and then they say something was wrong, they get a spin, and then the rocket blows up. Okay, if you read the book, this is what happened in the movie, and it's actually pretty accurate. If your cargo shifts, right, rockets normally spin, making them spin not really fast but slowly rotating around means that you actually even out any atmospheric effects, right? Instead of, if you have a little more drag on one side of the rocket than the other, the drag on one side will make your rocket veer off course because it's going to get going really fast. And so making it spin a little bit, not a lot, but a little bit, helps. A lot of spin, however, is a problem because then it starts doing weird things to the fuel in your tanks. So anyway, this is the same problem. This is the same problem as an ice skater, or you remember we talked about the guy on the spinning around, moving the weights in and out, right? Changing his angular velocity. So same kind of problem. All right, so let's do this. We're gonna need a whiteboard for this thing. Okay, so we have, this is going to be a conservation thing. So we're going to have a before and an after. Okay. Before, we had our rocket, and I'm going to say our rocket looks like, I don't know. This is going to go poorly. We're going to make a blue rocket. Okay, well, I'm drawing lines. I didn't want to do that. Okay, we have a rocket, right? Here's a rocket, and it's got like little things, and and it's got fire coming out the bottom. Okay. And before, it's rotating at so we'll use W, but I mean omega, right? It's got a 10 radians per second, right? And it's got a moment of inertia. We'll put little zeros here. Moment of inertia of 1,000 kilogram meters squared. Okay. Afterwards, we don't know its angular velocity, but we do know its moment of inertia changed to 1,500 kilogram meters squared. Okay, so conservation of angular momentum tells us that our angular momentum in the beginning has to equal our angular momentum at the end. So if we plug in values for that, we get, that means, because angular momentum is angular velocity times moment of inertia times angular velocity. Okay. And if we solve that for our moment of our angular velocity, because that's the final angular velocity, because that's the only thing we don't know, we get that it's equal to our initial moment of inertia times our initial angular velocity divided by our final moment of inertia, which we could plug in numbers, but we don't want to do that because we're not done yet. Because what we actually want is how much work was done. Okay? So work is what causes a change in kinetic energy, right? So we need to know how much kinetic energy changed. Okay, so our kinetic energy beforehand, oh, I didn't leave myself much space. Our kinetic energy beforehand is 1/2 times I, the initial angular velocity, initial moment of inertia times your initial angular velocity squared, right? Our final kinetic energy is the same thing, just with finals in there. 1/2 times our final moment of inertia times our final angular velocity squared, right? But we know our final angular velocity in terms of these other things we do know, right? So we can rewrite that. Our final kinetic energy is just 1/2 times our final moment of inertia times our initial moment of inertia squared times our initial angular velocity squared divided by our final moment of inertia squared. Okay? And if we clean that up a little bit, we get that our final kinetic energy is 1/2 times our initial moment of inertia squared divided by our final moment of inertia times our initial angular velocity squared. Okay, are you following me so far? Yes, no, maybe?
Maybe.
Maybe. Okay, so what have I done so far? Well, the first thing I did is I wrote out what I knew initially and what I knew at the end here, right? And then I came down here and I said, okay, I know that angular momentum is a conserved thing, right? Because this rocket wasn't touching anything, nothing applied a torque to it. And remember, torques change angular momentum, just like forces change linear momentum. So if there were no torques, then the angular momentum I had before and the angular momentum I had after have to be the same. Angular momentum is just moment of inertia times angular velocity. So I could use that to solve for my final angular momentum in terms of things I knew at the beginning. And this thing that my final moment of inertia. And then I said, okay, but what I actually want is the work done. And I remember from the work kinetic energy theorem that anytime I change kinetic energy, that means work had to be done. So here's my initial kinetic energy. Here's my final kinetic energy. And I already know what this thing is, what omega final is. So let's put that into here. And when I do that, and I do a little bit of algebra, I get something that looks like this, right? And I can even go one step further. I can write that my final kinetic energy, because if I look in here, I've got my initial kinetic energy, right? I've got a 1/2 initial moment of inertia times initial angular velocity squared. So this is the same thing as my initial kinetic energy times the ratio of my initial moment of inertia to my final moment of inertia. Okay? My initial moment of inertia was 1,000. My final was 1,500. So if I reduce those fractions, I get 2/3 here. So I lost 1/3 of my kinetic energy, which means that had to go into work, right? Negative work, because I lost energy. So where did that energy go? Bolt breaks loose, cargo moves around, increases the moment of inertia. The energy went out of kinetic energy, right? The rotational kinetic energy. Where did it go?
Potential energy,
What kind of potential energy?
mechanical, because that cargo could be moved back to where it was and it would do the positive work of accelerating its rotation.
That's right. But if it was a potential energy, remember, potential energies are special things, right? There's only 2 of them. There's in this class. There's gravitational potential energy, which this isn't, because, right, we didn't lift something up. Or there's spring potential energy, which probably also not, unless you had this on a spring. So what probably happened, right, if you're the spacecraft, is that some piece of your cargo slammed into the wall of your spacecraft, right? You took kinetic energy from rotation and gave it to a piece of your spacecraft, right? And that piece of its spacecraft happily went with that kinetic energy until it hit something, like, say, the wall of your spacecraft. And then you're in trouble. And that's why things go boom, is because you don't want things crashing around inside of your rocket. Okay? So if we actually wanted to ask how much work, right? Work is change in kinetic energy. So let me write that. Come over here. Work is K final minus K initial, right? And we know how to write K final in terms of K initial. So the work here is K initial times our initial moment of inertia divided by our final moment of inertia minus K initial, right? And if we keep simplifying, we get that our work is just, well, we figured out that our initial moment of inertia divided by our final is 2/3. So 2/3 of something minus something is negative 1/3. So it's negative our initial kinetic energy divided by 3. Which, if we plug in some numbers, right? Our initial kinetic energy was 1/2 times 1,000 times 10 squared. So 1/2 1/2 times 1,000 is 500. 500 times 10 is 5,000. 5,000 times 10 again is 50,000. So our work is 50,000 divided by 3 joules, which is a big number, right? That's a lot of energy, which is why you don't want to break your spacecraft. Okay, so what did we do here? We used rotational things, right? We had to use angular momentum to figure out how fast it was rotating after. And then we had to use rotational kinetic energy, and we had to use the work energy theorem. When we put all those things together, we got the answer, right? How much work was done. All right. Questions, comments, concerns? All right. Next up. All right. A ball with a mass of 1 kilogram and a radius of 0.5 meters is rolled up a hill with an initial velocity of 10 meters per second. The hill is 10 meters tall. Does the ball make it to the top of the hill? If so, how fast is it moving? If not, how high does it get? And the moment of inertia of a sphere is 2/5 mr squared. Anybody want to do this one? I'll take that as a no. All right, we're going to need our friend, the whiteboard again. Okay. So let's draw this thing. I've got a hill, right? There's my hill. Okay. My hill is 10 meters tall, right? Man, that is a terrible M. Okay, my hill is 10 meters tall. Okay, I have a ball. Right? And it's got a radius, a mass of 1 kilogram, well, and a radius of 0.5 meter, 0.5 meters. Okay? And it's rolled up a hill. Okay? So it's got some initial velocity. It's moving up the hill. It's got some initial velocity of 10 meters per second. All right. The hill's 10 meters tall. Does it make it to the top of the hill? Well, how would we figure that out? Davey, it looks like you just said something, but for some reason I still can't hear you. Can everybody else hear him?
Yeah.
Weird. That's a new one for me. Okay. Anybody want to repeat what he said so that I can hear it? Oh, he put it in the chat. Okay, you have to use the initial velocity and use the acceleration of gravity. We could do that, but that's actually going to be hard because it's rolling, which means it has a friction force, right? So it's not just gravity that's going to be doing it. It's also going to be the friction force. But it turns out we can make our lives a little bit easier if we do this with energy. Okay. So if we do this with energy, we can write our energy before, right? Which is two types of kinetic, right? We've got a 1/2 mv initial squared. Oh, wait. Plus 1/2 moment of inertia times our angular velocity initial squared, right? Here's our linear kinetic energy. Here's our rotational kinetic energy. And at the top of the hill, or at its highest point, it's going to have potential energy of mgh, right? All right, so now let's start plugging things in here. We've got 1/2 mv naught squared. And we know the moment of inertia, right? The moment of inertia is 2/5. So 1/2 times 2/5 is what? Come on. Fraction people. 1/2 times 2/5.
1/5.
Yeah, there you go. So what we're going to end up with is this, right? We've got 1/2 mv naught squared plus 1/5 m r squared omega naught squared. And if we're clever, we recognize that this right here is what? Sorry, I was trying to circle it, but I kind of wrote through it. What's r times omega?
Angular velocity.
Well, omega is angular velocity, but if I multiply it by a radius, what do I get? Hey, by the way, I heard you that time.
I
Weird.
left and came back and it worked.
So what are the units on angular velocity?
Radians per second.
Yep, radians per second. And if I multiply a radian by a radius, I get
Meters per second.
yeah, I get a velocity. So I can rewrite this whole thing, right, as 1/2 mv naught squared plus 1/5 mv naught squared. Or in other words, if I combine my fractions, 1/2 plus 1/5 is what? 7/10. That's not bad. Okay, that's how much kinetic energy I have. Now, I want to know how high I can get. So I'm just going to set this equal to mgh. And we'll see if h is bigger or smaller than 10 meters. So if I do that, let's do it in a different color over here, right? I get mgh equals 7/10 mv naught squared. The masses cancel out, so it doesn't matter how much mass this thing has. I'm solving for h, so I get that h is equal to 7, well, let me write it this way, 7 mv naught squared divided by 10 g. Okay, now, oh wait, I got rid of the m. No m here. I can't get rid of the m. Okay, let me just scribble it out. No m. Make it go away. Bad m. All right. So my V naught is 10, right? So I've got 7 times 10 squared, which is 100. So 700 in the numerator. And 10 times G, well, G is basically 10. So that's 100. So I get that my H was 700 divided by 100, which is 7 meters. Which means that does it make it to the top of the hill?
No.
No, right? It only makes it up 7 meters. Great. We've already answered it, right? If not, how high does it get? 7 meters. Voila. Now, here's your bonus question. Is there a shape of the same mass and radius that would make it to the top of the hill? What does the shape do? If I don't change the mass and the radius, what does changing the shape do?
It changes the moment of inertia.
Yeah, it changes this number out here, right? It changes this number, right? So what's the biggest number I could put in front of those two?
1.
Yeah, because that would mean that I had an infinitely thin ring of radius r. So if I put a 1 in here instead of a 2/5, I'd get a half, which means I'd get a half plus a half, which means I'd get 1 over here instead of 7/10. And if I get a 1 over here, that means I just get V naught divided by G. And V naught is 10, G is basically 10. So then my height would equal 10 meters. So the answer is yes. If I move, if this were a ring, it could roll all the way up the hill. If it's not a ring, if it's a sphere or a disc or something like that, it won't make it all the way to the top of the hill, which is kind of cool. All right, let's do one more. Are we good for one more?
Yeah.
All right. Let me turn off my whiteboard here somehow. And, oh, this one's a good one. Okay, I'm not actually going to make you do this one. This is a good problem though. So what kind of problem is this? Just read it for a second. Let it wash over you. What kind of problem is this?
It's a torque problem.
Yeah, it's a torque problem. And the torque is the cross product of radius and force, right? So if I draw the radius vector in here, my radius vector looks like that. And it's going to change, right? As this thing rotates, that radius vector is going to change length and it's going to change angle. Okay? So it turns out that the biggest torque you can get is when the block is oriented. Let me draw this. The biggest one is when the block is oriented like this. And the reason for that, I'm sorry, the smallest is when it's like that. And the reason for this is that at that point, your force vector is straight down and your radius vector is there, and the angle between them is 45 degrees. Okay? the biggest, that's the smallest. The biggest is over here. I'll draw it over here. The biggest is when, no, I can't. Oh, hey, they have a thing for that. Cool. The biggest is when it's oriented like this, okay? And it should be filled in, right? But this thing doesn't have a way to make it filled in easily. So in that case, your force vector is still pointed straight down, and your radius vector is pointed like that, which means it's perpendicular, which means an angle of 90 degrees between them, which is the biggest you can possibly have. Okay. All right. This one got kicked off my exams because it's too hard. So I'll stop with that one. All right, let's talk about one more. All right, anybody want to take a run at this one? All right, what forces are acting on this guy? Draw me a free body diagram. Come on, you guys have been drawing free body diagrams in your sleep. Well, there you go. Hey, there you go. We got tension force and we got weights. Wonderful. Okay, somebody else. Which way is this thing accelerating? It's moving in a circle, right?
It's accelerating inward.
Yeah, it's got to accelerate towards, there we go, towards the center of the circle, right? Because if it's not accelerating towards the center of the circle, it wouldn't move in a circle. It would move in a straight line. Okay, so how do I get an acceleration towards the center of the circle out of those two forces? Well, the answer is, let's see. I take my tension force and I break it into components, right? I've got like a component going in that way, and I've got like a component going up this way. And that's my tension force. And this vertical component of my tension force has to balance this component of gravity, right? So writing that out in math, I get that my tension force times the, I need to define an angle here. Let's call the angle be the angle here, the angle between the horizontal and the tension, right? So I'm going to get that my tension force times the sine of my angle, which I'm going to call Q, because I don't have a theta on my keyboard, which is a shame, by the way. We should all have thetas on our keyboards, right? That has to balance the weight. Okay. What about the horizontal component? What does that do? Well, that causes an acceleration, right? So Newton's second law says the sum of the forces equals mass times acceleration. Okay, well, I can solve for t and plug it in there. And if I do that, I get that t is mg divided by sine q, right? I plug that into the horizontal equation, and that means I get well, come on, mg cosine q divided by sine q equals ma. The masses cancel, and I'm left with my acceleration is g cosine q divided by sine q. Okay, but that's not what the question asked, right? The question asked, find the tension in the rope as a function of the mass, the rope length, and the time it takes for the mass to make a complete circle. So I've got a problem here, right? Because the length of the rope is right up here, right? That's L. How do I relate this angle to that length? Because my tension force over here doesn't have length, it doesn't have length in it, or the time it takes for the mass to make a circle. It has an angle. So what do we do? Well, if I had a triangle, I could do something, right? So let's come over here and let's draw a triangle. So I've got a triangle right there. Oh, wait, I don't want arrows. I want just lines. I can draw a triangle from there to there, there to there, and there to there, right? And if I drew it right, it would be a right triangle. And this corner has my angle in it, right? That's Q. Let's put Q here. There's not a lot of space for Q. Okay. So, and I've got sine here, but I could just as easily have cosine. What is this length of the triangle? The bottom length. What's this?
Would be the radius.
Yeah, it's the radius of our circle, right? So that means I could come over here and I could say, okay, the cosine of Q is equal to the radius of our circle divided by the length of the string or the rope, right? Well, that gave me a way to get rid of Q, but it doesn't actually help me get rid of, but I've introduced a new problem because now I've got radius. So where does radius show up when we're talking about things moving in circles?
Right. 2 pi r.
Yeah, okay, so its distance it travels is 2 pi r. It's, if I divide that by the time it takes t, right? Now I've got my velocity. Let's write that down. So my velocity is 2 pi r divided by t. Oh, wait, I'm using t twice. Dang it. Let's relabel things. Not t. We're going to make the time it takes to complete a circle be P for period. Okay, so rewriting that, I know that my velocity is 2 pi r divided by P, right? And it turns out that I've got something over here that I can use. I've got this thing, right? Because my acceleration is a centripetal acceleration. And a centripetal acceleration has magnitude v squared divided by r, right? Which means if I plug this whole thing in, because v is 2 pi r over p, I'm going to get 4 pi squared r divided by p squared. My acceleration is equal to that, okay? Which is good because now I'm done. Doesn't look like it yet, but I am, right? Because I can get R in terms of Q and L. I've got T in terms of Q. So we're golden. Okay, there's a lot of algebra left. We're running short on time. Do you want me to do the algebra?
Sure.
All right, let's do the algebra. So I'm going to do this on paper because it's going to get messy if I try to keep doing it on here. So let me come over here. Oh, and I'm going to have to turn off my virtual background here. My lovely campus scene. All right. So we had equations, right? We knew that our tension force was equal to mg over sine theta, right? We knew that our acceleration was 4 pi squared r over p squared. We had a triangle. Here's theta, here's r, here's L. This side is L squared minus R squared, right? And further, we knew that our so let's see. If we wanted to rewrite R in terms of L, right? Wait. And we knew that our acceleration was equal to T sine theta, cosine theta over M, right? Okay, so now it's just fun with algebra. Cosine theta is R over L, right? And acceleration is 4 pi squared R over P squared. So this is going to be T over M times R over L. Our R's cancel. And there we go. Our tension force is 4 pi squared ML over P squared. Bam. How are we feeling?
Good.
Good. All right. I think we're probably out of time for today. So here's what I'll do. I will send out another email. We're going to do the same game on Friday where we're going to keep reviewing. And so I will send out an email that has a link to those slides. You are more than welcome to prepare a solution and then come to class ready to talk about it, and I'll give you more extra credit, and everybody can go again on Friday. I'll get special thank you to Davey and Mario who presented today. And yeah, I'll see you on Friday.
Can we present again for more credit? 'Cause the
Yes.
next day? Nice.
Yes, you can.